Chapter 11, Problem number 12. A bullet of mass m is shot at a hinged rod and hits the rod at a distance d from the hinge. The rod was initially at rest and has a moment of inertia of I about an axis through its hinge. The bullet is fired at an angle theta to the rod, as shown in the top view, with an initial velocity of v at a distance d from the hinge. The angular speed of the rod with the bullet embedded right after the collision is omega. Several students discussing this situation state. Anne says the angular momentum of the rod plus bullet about the hinge after the bullet is embedded is the same as the initial angular momentum of the bullet about the hinge. Bella says the kinetic energy of the bullet before the collision with the rod is equal to the rotational kinetic energy of the rod and bullet together after the bullet hits the rod. And Carlos says the bullet is going straight, so it does not have any angular momentum about the rod hinge before the collision, so we need to use conservation of energy. However, we really can't compare energies before and after, since we do not know how much energy is lost in heat, deformation of the bullet rod, and sound. Which of any of these students do you agree with and think is correct? Explain your reasoning. So, I'm going to tackle a couple of things first. Bella is not correct, because we know that the energy is not conserved. This is a non-elastic collision, and we know that there is, in fact, some energy lost. In fact, Carlos says nicely, we can't compare energies before and after, since we don't know how much energy is lost in deformation of the bullet and rod, and of sound emitted, and heat, and so on. So Carlos 100% right on that. Where Carlos, unfortunately, also goes wrong is this is not true. The bullet going straight does not have angular momentum about the rod hinge is not true. An object traveling in a straight line past a point of rotation has an angular momentum whose magnitude is given by the moment arm of the momentum vector times the size of the momentum vector. So we would do something like extend this to say this is the moment arm of the momentum, and then there would be this distance would be r perpendicular, and so there is angular momentum even though it's moving in a straight line. This comes back to the idea that angular momentum is sort of was discovered with things spinning, but is actually a deeper thing, and even things that aren't spinning can possess angular momentum. Therefore, Carlos is sort of out too. In fact, it will be Anne who's correct, because there is no external torque, and we know that the change of L with respect to time is equal to the external torque, along the same lines that the change in momentum with respect to time was the force. And so, since there is no external torque, then there's no change in angular momentum. And so the angular momentum will be conserved, and so we can say this is true, which would allow us to actually compute the speed, although they don't ask us to do that.